Okay, I think we're gonna start now. So hello everyone. Welcome to Math Divulged Week 1 seminar. This is a seminar on calculus. Thank you all for coming. I'm going to be your teacher today. My name is Benjamin Wright. I've done a lot of math. I've been to mock twice in high school, and I'm going to MIT in this fall as a freshman. Your TA for this class will be Kevin Chang. Kevin, do you want to introduce yourself?
Hello, I'm Kevin Chang. I TA'd for our Wednesday class this week, and I will be going to Caltech next fall for college.
Okay, so I'll be teaching and I won't really have time to answer questions. So if you could direct all your questions to Kevin, and if Kevin can't handle them, then you can also go to Brian Liu. So today we're going to try and teach you guys a pretty solid introduction to calculus in 1 hour. But since it's only 1 hour, it's going to be hard to teach everything rigorously and give you a really good understanding. So this isn't a substitute for a class, but it's meant to, give you like as much of the basics as I can in 1 hour. We have a handout available on the website, so you can go and check that out. It may help you follow along easier. Okay. Let's get this whiteboard going. Okay, so one of the biggest foundations of calculus are derivatives. But to teach derivatives, we first kind of have to go through what limits are. So limits. Limits are something that's used to make calculus rigorous. Whenever you want to prove something and you want to prove it well, you go through limits. Okay, wait, this is a problem. So the notation you use in a limit is you do something like this. What this notation means is you're looking at a function f of x. F of x. It's a function, and you have a x value of a. And you take points on this function getting closer and closer to a. And then you look at all the values you get, all these f values. And the value of f that you get infinitely close to, that's your limit. So when f is a continuous function, like this, the limit is actually equal to just plugging in the value. But this is only when your function is like nice or continuous. Or when I say nice, I mean continuous. When f is not continuous, we're not going to be really dealing with those cases in this class. But I should probably still give you an example. Sorry, some technical difficulties. Okay, so an example of when f is not continuous is something like this. You go up, up, and up, and up, and then you have a jump to right here. And then you jump back down, and you keep going. And let's say that this value is like 6, and the value up here is like 10. then this x value over here is like 4. Then in this case, when you take the limit as x approaches 4 of f of x, you actually get 6. Because as you take values getting infinitely closer, your f value becomes infinitely close to 6. That's why the limit is 6. Your values are limiting towards 6 is the vocabulary you'd use. So even if the actual value at 4 is 10, because in a small distance around it, you get roughly 6, the limit stays 6. So the actual value does not actually matter. But of course, we're not going to be really dealing with like weird functions like this. We're going to be mostly dealing with nice continuous functions on the left. Okay. So those are limits. The next step will be instantaneous slope, or first of all, slope. In case you haven't ever calculated slope before, if you have 2 points, one is AB and the other is CD, the slope between them is rise over 1, which is D minus B over C minus A. This is the change in Y over the change in X. So what instantaneous slope is when you have a function and you're meant to find the slope at a specific point, not between 2 points of the function, but just 1 point in the function. So if I draw a function, if I want to find the slope at precisely this point, what is it? So the most intuitive answer is I just draw a tangent line, a line that only intersects the function once at exactly that point, and I find the slope of that tangent line. That's the easiest way to think about it. There's another way to think about it, which is you take 2 points which are very close to each other, and you take the slope between those 2 points, and then you move that second point very, very close to the first point. And you keep moving those 2 points together until those 2 points overlap. And then you only get, once again, you get a line that only intersects the function at one specific point. So that's instantaneous slope. Oops. Technical difficulties. Does anyone know how to turn off attendee screen sharing?
You should be good now, Ben.
I'm good. Okay.
Yes.
Okay. I'm gonna keep going then. Okay. So now we can finally move on to derivatives. So derivatives are intimately connected with instantaneous slope and are kind of almost the same thing. So there's many different ways, there's many different notations for derivatives. For now, I'm just going to use this prime notation. I'm going to write f of x, but I'm going to put this prime up here. And that's going to mark the derivative. So f prime of x, the derivative, it just outputs the instantaneous slope at each point. Instantaneous slope. So f prime of x is a function. So if I were to be more rigorous using limits, I would do this. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. If you remember, one of my definitions of instantaneous slope was I take 2 points that are very close to each other and take the slope between those two. That's exactly what I'm doing here. If this left point is x comma f of x, and this right point is x plus h comma f of x plus h, then if I use the slope formula on this left over here, and apply it to these 2 points that are very close to each other, I get this. This thing is just a slope formula. But we need those 2 points to go very, very close to each other, or essentially be the same point, which is why you have to take a limit and make h, the gap between the points, go to 0. So this is the formal definition. You won't often need to use this. If you want to prove what the derivative of something is, you will come back to this. But if you just want an intuitive understanding, just think of it as taking the derivative or the slope at each point. So let me give some examples so what a derivative is becomes a bit more clear. If you take a function f of x is equal to 1 plus 2x, this is just a line. It starts at a 1, goes up with a slope of 2. And you look at f prime of x. F prime of x outputs the slope at every single point, but we know that this is a line, so the slope everywhere is just 2. Therefore, the derivative just equals 2, no matter which point you're at. That's a pretty easy example. If g of x is equal to 0, stays horizontal, then g prime of x would also equal 0, because the slope of a horizontal flat line is still 0. In fact, even if you add a constant to g, like 5, the derivative stays 0. That makes intuitive sense, right? If you shift the whole function up by just a constant, it doesn't actually affect the slope that things are going at, so it doesn't affect the derivative. Okay, hopefully you guys understand what the derivative is. If you guys don't, you should really ask the TAs for help. They're nice and are here to help you. Now we can go through different notation. So the problem with derivatives is that a couple of people kind of encountered them or came to the conclusion about derivatives on their own, and they each came up with their own notation. And different notation is useful in different circumstances. So sometimes we kind of have to cycle between different methods. So one, we just use that prime method I used before. Another one is I use d over dx and then of f of x. So what this notation means is this d over dx thing on the left is like an operator we apply to f of x. To explain that, so yeah, I think you can explain it with the third notation at the same time. So the third notation is very similar, but you just have df in the top and dx in the bottom. The third one is a bit more intuitive. If you remember from our formal definition over here, we have a limit of a small change in f at the top over a small change in x at the bottom. So that's what this means. D just means a small change, roughly. So the slope, it makes sense that it's just a small change in f over a small change in x. And for vector notation for number 2, that's why d over dx can be treated as a derivative function of functions. There's actually a fourth way, which is using Heaviside notation, which is just a big D then an F. We're not going to actually use this, but some people use it, not many. Okay, so That's derivatives. Now we're going to go through some common derivatives. Just knowing what derivatives are doesn't really help you much. You need to be able to take derivatives of things. And taking derivatives, you kind of need to learn a few basic derivatives and then learn some rules. And from there, you can kind of find the derivatives of almost everything. So, common derivatives. Perhaps the most common of them of all is if you look at f of x is the polynomial. We're going to just take x to the n. If you want to find how to take the derivative of this, I'm going to go back to the formal definition. F prime of x is equal to the limit as h approaches 0 of x plus h to the n minus x to the n over h. So we can treat h as something that's very, very close to 0. So what that means is when we expand this fraction, if we have something that's multiplied by h, you're multiplying by 0 essentially, so that term vanishes. So you only care about terms that don't have an h with multiplied by them. We have one h in the denominator, which means we can cancel out at most one h in the top per term. So we're only looking at terms in the numerator that are just powers of x or powers of x times 1h. The way we're going to do this is we're going to expand this using the binomial theorem. If you don't know what the binomial theorem is, that's fine. All you have to, you can just take it for granted that if you take x plus h to the n and you can expand it and you get x to the n plus n times x to the n minus 1 times h plus, and then you have more terms, but each of these has an h squared in it. So I can write it like this, h squared times other terms. So if you plug this into over here, you get that the x to the n over here and the x to the n over here will cancel out. So all we're left with is n times x to the n minus 1 times h. Then we have plus h squared times some other things. Then we divide by h. But if you remember, I said that the terms with an extra h after you divide everything out, you're multiplying by 0, so we don't care about those. So all these terms with h squared, actually, we don't care about them. They'll just be 0 afterwards. So you can continue this to limit of h goes to 0 of n times x to the n minus 1. Remember, this h in the top and this h at the bottom canceled out. At this point, the limit doesn't actually do anything. So we just get this, n times x to the n minus 1. This is a very powerful result. It turns out that this works even if n is not an integer. This actually works for all n real. As long as n is a real number, you can apply this derivative formula to it. It's just, let's give some examples. If f of x is 1 over x, which is equal to x to negative 1 power, then f prime of x is equal to, so we pull this negative 1 down, and then we reduce the exponent by 1. So negative 1 to the x times x to negative 2, which is actually negative 1 over x squared. This is true. So we can apply this to essentially every polynomial. If you want to apply this to like polynomials with multiple terms, for example, maybe f of x is like 2x to the n plus 5x to the n minus 1 plus 6x or something like that. We just apply the derivative to each individual term. 2n x to n minus 1 plus 5 n minus 1 x to the n minus 2 plus 6. It may not be clear why why you can just do this, like why you can just add derivatives like this. I guess one way you can think about it is if you have two functions, one's going up at the slope of a certain amount and one's going up at the slope of another amount, when you add them together, you just get like the slopes add as well. That's something you're just gonna have to intuit, and we'll just have to assume here. Okay, so this is so that's the first common derivative. The second common derivative we're going to do is exponents. We're going to try f of x is equal to e to the x. E is a very special number, but what matters now is that e is just a constant. It's like e is roughly 2.7, and e can be defined in multiple ways. But one of the properties that we're going to assume, and that's the most valuable right now, is that e to the x is roughly 1 plus x for small x. If we were to graph it, e to the x would look something like this. And if we take the tangent line at x equals 0, this line 1 plus x is tangent right there, and it's a very, very close approximation. So when we use the formula for the derivative f prime of x, we get e to the x plus h minus e to the x over h. So we know h is very small. So what we can actually do is we can split e to the x plus h into e to the x times e to the h. And then we plug in this e to the x is roughly 1 plus x for small x. So this is e to the x times h plus 1 minus e to the x over h. Now, if you notice, this e to the x term cancels out with this 1, and then we just have e to the x times h at the top, and then this h cancels out with this h. So we actually just get e to the x. This is also a very powerful result, because we get that f prime of x is actually equal to f of x here, which is equal to e to the x. So e to the x is a function where if you take the derivative, nothing happens to it. And that's really marvelous and pretty cool. If you want a more rigorous proof, you'll probably have to go somewhere else. It's not really in the scope of this class, unfortunately. So an application of this is when we want to talk about the natural log. F of x is equal to ln of x. So this is actually the inverse function of e to the x. Ln of e to the x is equal to 1. So this is equivalent to log base e of x. If you guys don't know what logarithms are, that's fine as well. Just think of it as if you have e to the x over here, just think about reflecting this graph over y equals x, then you get something like this. And that's ln of x. You're just reflecting over this diagonal line. So how are we going to find the derivative of this natural log of x? You guys should think about it for a second. It's a challenge, a puzzle I'll give you. In around a minute, I'll just show you the answer. Okay, I'm going to go ahead and go with it. So if you, the most important thing you need to notice to find the derivative of ln of x is that when you have a line and you reflect it over y equals x, the slope becomes very special. If the slope of this first line is m, the slope of the reflected line is 1 over m. Like these angles match and the slopes are almost the same, but you just flip x and y. So if you look at the slope formula is like a small change in y over small change in x. Since flipping across y equals x just flips x and y, this becomes delta x over delta y, which is kind of an explanation as to why it just becomes 1 over m. You're literally just flipping it. So what that means is if you have a point on e to the x and you take a tangent line and you have that same point reflected and you look at the slope of that tangent line, the slopes actually get like multiplicatively inversed or reciprocated is the word for it. So that's how we can relate the slopes of e to the x to the slopes of ln of x. So that might make you think, hey, maybe f prime of x is just 1 over e to the x. Because, hey, we know that the slope of e to the x is e to the x. So the slope of ln of x is just 1 over that, right? Isn't that what you just told me? When you reflect the line, you get 1 over the slope. So there's a problem with that logic. Like, this is wrong. And the reason is when you reflect over y equals x, your x value changes. So you can actually use the same x here. The slope at this point on ln of x is 1 over the slope at this point on e to the x. But since those points don't have the same x value, you can't do this. Instead, what you need to do is slope of e to the x at x equals a is e to the a. And therefore, the slope of ln of x at y equals a is 1 over e to the a. So I changed e to the x to, I changed x equals a to y equals a. And that's because flipping over y equals x flips the x and y coordinate. So if this over here is x equals a, then when we reflect, we actually get on the line y equals a. So what we have to figure out now is when y equals a on ln of x, what is x? So ln of x equals a. Well, we know that ln is actually the inverse function of e to the x. So ln is just doing the opposite of e to the x. So this tells us that x is actually e to the a. So the slope at x equals e to the a is 1 over e to the a. That just tells us that the slope of ln of x, f prime of x, is actually just 1 over x. Because you plug in the input and you just reciprocate it, and that's your slope. Whoa, 1 over x. And this actually has an interesting connection with our polynomial derivatives before. If you remember, our d over dx of x to the n was n times x to the n minus 1. So this over here is also a polynomial. So you might think there may be some overlap. There's actually no overlap, because when we get an exponent of -1 after taking derivative, it actually turns out to be 0. Okay, like, so for this exponent to be -1, we need n to have been 0. So that just means we're taking the derivative of x to the 0, which is 0 times x to -1. The problem is you have a 0 here, so that just cancels this whole thing out and you get 0. So you can actually never get 1 over x or similar things as your derivative from polynomials. You have to go through ln of x. And that's why ln of x is pretty important, because you can't get it through derivatives. Okay, so that's ln of x. Our next case is trigonometry, sine and cosine. So what is d over dx of sine of x? And what is d over dx of cosine of x? Hopefully you guys know what sine and cosine are. If you don't, I can just derive them right now, or just define them right now. So if I have a circle with radius 1 about the unit circle, then a point is cosine x comma sine x if this angle over here is angle x in radians. So angle x in radians gives us the point cosine x comma sine x. So sine of x is like the height and cosine of x is like the x position. So if you want to find the derivatives, how are we going to do this? We can, your first step from your intuition might be to try and graph what sine and cosine are. So maybe we can try that. So this is sine. But if you look at this and then you realize I have absolutely no idea what these slopes are. How do we do this? And then you move on, and then you realize, hey, maybe I can plug in this limit, the formal definition of derivatives. So you get sine of x plus h minus sine of x over h. Then you look at this and you realize you have absolutely no idea how to deal with the sine of x plus h term, and then you just give up. So we have to find a more clever way, maybe a more geometric, interesting way of finding out the derivatives of sine and cosine. And the way we do it is we go back to this definition of sine and cosine on the unit circle. Let me draw a much bigger diagram. So I'm gonna turn this into a word problem. So you start at 1, 0, and then you walk along the circle at 1 unit per second. So you're walking along the circle 1 unit per second. So your position at time t is actually equal to cosine of t comma sine of t. That's because the way radians are defined is that on the unit circle, if you walk a certain number of units around the circle, you've actually crossed that many radians in angles as well. That's a nice thing about radians. You can kind of just equate distance on the circumcircle to angles on the unit circle. So what we're going to look at is if we're at a point here, maybe that's not the best point. Okay, let's look right over here. We've noticed before that derivatives are pretty much equal to instantaneous slope. So maybe looking at the slope of this circle at each point will help us. So, but I'm gonna actually word it in a different way. Instead of slope, let's actually look at speed or velocity in particular. At this point, we're moving in a direction perpendicular to the radius. And we know that the length of this vector or your speed is actually is 1. Your speed is 1. And then the direction is perpendicular. So we know that this point is cosine t comma sine t. And perpendicular to that is this vector negative sine t comma cosine t. This just comes from the fact that like if you have a slope m, then the perpendicular slope is -1/m. Like if I give you a graph, if you have a slope of 2, the slope of something that's perpendicular is -1/2, just like that. So we know that a line going negative sine of t in the x direction and positive cosine of t in the y direction is perpendicular to a line going cosine of t in the x direction and sine of t in the y direction. So our velocity is negative sine t, comma cosine t per second. So if you guys aren't familiar with vectors, what I've just said may be very confusing. So ask a TA, or maybe I can try and define this a bit easier. Okay, let's do this. Your x velocity is negative sine t, and your y velocity is cosine of t. And the reason is because we need the x velocity, we need the total velocity to be 1, and we know that we need the direction to be perpendicular to the radius. So if you guys know anything about trigonometry, you know that sine squared of t plus cosine squared of t is equal to 1. So that matches the condition that the total velocity is 1. And we've already shown through this perpendicular slope thing that this is actually perpendicular to the radius. So it turns out that these are exactly true. So what does this tell us about derivatives? Well, we know that your x position follows the path of cosine of t, and we're just given that the velocity of that is negative sine. We're just given that your x velocity is negative sine t, and your y velocity is your y position is sine t, and your y velocity is cosine t. So I'm going to give you guys like a minute or two to think about this. Can you guys figure out what the velocities of cosine and sine are from this? Okay, I've kind of already spelled it out to you. So, if we have, if we look at the x and y coordinates together, maybe this may not be too intuitive, but if you just isolate the x value, if you look at just this function f sub x of t is cosine of t, and we know that the velocity or speed is negative sine t of this function. But when I say velocity or speed, what that actually means is rate of change. That's what speed is, right? Just like how fast you change in a specific time, which is negative sine t. It turns out that this rate of change is actually the exact same as your definition of a derivative. If I need to explain that a bit more, you can think of derivatives as, remember, a small change in your function over a small change in your variable. But that's just change in rise over change in run. This is just like, or you can think of it as like a distance over time. So the derivative is actually equal to the speed or rate of change in this situation. So the derivative of cosine is actually just negative sine of t. And similarly, the derivative of sine of t is just cosine of t. So let me write that all out again. D over dx of sine of t is equal to cosine of t. And d over dt of cosine of t is negative sine of t. If you notice, I use t here instead of x. It actually does not matter which variable you use. The variable you put here in the bottom just tells you which function you're taking the derivative with respect to. Like you can replace all these t's with x's and it's the exact same thing. So this is the foundation of trigonometry and calculus. Okay, so I've given you a lot of common derivatives, but I haven't exactly taught you how to be more creative in your derivatives. For example, what happens if I give you a function like x cubed plus x over x squared minus 1 or something like that? Like how would you take the derivative of a function like this? Or for another example, how do you take the derivative of a function like sine of 5t? Like you've been taught sine of t, but what about sine of 5t? It turns out that there's some very, very powerful tools with taking derivatives that will help you a lot. The probably the most important one is chain rule. So if you look at the handout, if you have the handout out, it'll tell you something like this: df over dx is equal to df over dg times dg over dx. I'm writing it this way with this notation because it's the easiest to see. Like as it is now, it looks like if you just cancel out this dg in the denominator over here and the dg in the numerator over here, if you just cancel these out, then it's the same. So this should be obvious. And that's exactly why I wrote it this way. If you think of derivatives as like a small change in f over a small change in x, then you can kind of like non-rigorously cancel stuff out like this. So that's kind of an intuitive reason for why this is true, but perhaps I should explain more about what this is. Let me give an example. Let's say f of, why don't I just use this sine of 5t example over here. Let's let f of x be sine of 5x. And we know how to take the derivative of sine of x, but we don't know sine of 5x. So what we're actually going to do is we're going to take g of x to be 5x. And then f of x is actually just sine of g of x. So if you want to take the derivative, of sine of 5x for dx, we can actually just do this: d sine of g over dg times d 5x over dx. And now we can actually do this. And the reason why we can do this is, first off, we know how to calculate the derivative of sine of just g. And we know to calculate the derivative of 5x. And then each of these individual derivatives use the same variable. Like both of the numerator and denominator use g. And that's very important. It's hard to take derivatives when you're using different variables. So we use chain rule to make sure that the numerator and denominator use the same variable. So this here, we know that the derivative of sine of x is just cosine of x. So we get cosine of g. And from here, we know the derivative of 5x is just 5, using our polynomial rules. So we can plug in what g was, and g was 5x, so we get this. So the derivative of sine of 5x is just 5 cosine 5x. So that's the use of chain rule. We're going to move on. Chain rule is very important though, so if you have any confusion, please just ask the TA. Like, chain rule is probably one of the most important things you can learn from this class. Our next rule is going to be product rule. Product rule. So product rule will tell you something like this. F times g prime is equal to f times g prime plus f prime times g. Essentially, if you want to take the derivative of a product of two functions, you use product rule. Let me give an example. Let's say you want to take the derivative of sine times cosine. Sine of x times cosine of x prime. Well, this is just sine of x times cosine of x prime plus sine of x prime times cosine of x, which is sine of x times negative sine of x plus cosine of x times cosine of x, which is just cosine squared x minus sine squared x. And there you go. That's how you find the derivative of that. Now, the neat thing about this is if you know some trig rules, you can realize that sine of x times cosine of x is actually just sine of 2x over 2 prime. And then if you use chain rule before, we know that if we have a number inside, you can just take the derivative as normal, but you pull out the 2. So chain rule will tell you that this is just 2 times cosine of 2t, or 2x, sorry, all over 2. And then the 2's cancel out, and you just get cosine of 2x. And there's actually a trig identity that tells you that cosine of 2x is actually equal to this thing. So it turns out this problem of taking the derivative of sine of x times cosine of x, you can solve through either the product rule or through chain rule. So that's pretty cool. That's, again, one of the reasons why I like chain rule. You can solve so many things through it. So the last rule is quotient rule. So I actually find quotient rule to be like not as important to remember because you can actually derive quotient rule through product rule and chain rule. But I'm still going to write out so you can remember it. So I'm not going to prove it. Quotient rule, if you have f over g prime, this is the rule. These ones here are primes. Well, this is just a squared. So this is g squared. This isn't like g double derivative or anything. It's just normal g squared. I guess, yeah, that's a problem with notation. Sometimes it doesn't look the best, but this is what it is. if you're so the way you would prove this is by treating the dividing by g as multiplying by 1/g. Then you just apply product rule and you figure out what the derivative of 1/g is. So that's how you would prove it. But I'm not going to go through that. Okay, now we're going to go into integrals. So integrals are the other part of calculus besides derivatives. But integrals are actually, to me, like once you understand derivatives really well, integrals come pretty obviously. And the way we do that is we first define what's called an antiderivative. Is the antiderivative of f. And what this means is that, you're literally just doing the opposite of a derivative. So that, like, if you take a derivative of the antiderivative, you just get f again. Okay, I'm replacing the with a because actually there are infinite antiderivatives. And those antiderivatives is just the same function, but you can add on any constant, because adding on a constant doesn't change your derivative. So all your antiderivatives is just f a of x and then plus some constant. So as an example, if f of x is like 5, then f a of x is 5x. Okay, so now integrals. So if I draw this very, very fancy S-type symbol, what does this mean? This might be scary. Maybe you've seen this before. So if you graph f, all that this tells us actually is that this scary symbol is just the area under the curve from A to B. This shaded area. That's what the integral is. That's all it is. It's really just this area from A to B. So how does that relate to antiderivatives, you say? Well, let's try taking the derivative. Let's try taking the derivative of an integral. So remember, integrals are area from A to B. So if we take the derivative of this, well, the derivative is, like I said before, you can think of a derivative as the rate of change. So if we have I apologize. I wrote that a bit wrong. So you can't actually write d of x. I'm going to use a different variable, d over dt, and a to t. Okay, so now our variable is actually the bound. So if we have a function, this a is fixed, but your next value can be like variable. So if we look at the rate of change of this area, if t increases a little bit, like if t goes from here to t plus dt, then how much does the area change? The area changes by this small sliver. So this is actually equal to sliver over dt. So what's the area of the sliver? So if you zoom in on the sliver a lot, you'll see something like this. You have a small bit of the function here, and you have a really, really long and thin, almost rectangle. In fact, we're going to treat this exactly as a rectangle. This will be f of t. This over here will be dt. And then any curve here will be negligible because dt is so small, this is essentially a rectangle. So the sliver area is actually f of t times dt. Then when we divide out by dt, these things cancel out, and you just get f of t. Okay, so the most important step of this is going from the integral to over here. Just, I guess, try and understand why taking the derivative of the integral gives you the area of the sliver over dt. You can ask a TA if you have questions. Okay, so what this tells you is that taking the derivative of the integral just gives you the function back. So it turns out that taking an integral is actually very, very related to taking an antiderivative. And in fact, the exact way they're related is if you have two bounds and you take a derivative like this is actually equal to the antiderivative at b minus the antiderivative at a. And this is the fundamental theorem of calculus. So these two antiderivatives have to be the same thing. So let's take an example. Let's say you want to find the area underneath the curve of x squared dx, which is a quadratic. It's like this. We have to give bounds. So let's just say from like 0 to 4. So that would be this region. So how do you do that? Well, what's an antiderivative of x squared? One antiderivative of x squared would be like 1/3 x cubed. Because if you apply the polynomial derivative rule that I showed earlier, the derivative of 1/3 x cubed just gives you x squared. So we could have used other antiderivatives. For example, 1/3 x cubed plus 10 would also work. The thing is, adding a constant doesn't actually change its final value because since you're just subtracting two values, the constant gets subtracted out. So we can just use this antiderivative and accept that we'll get the same no matter which one we choose. So this is 1/3 of 4 cubed minus 1/3 of 0 cubed, because you have to plug in the bounds into our antiderivative. So this just actually gives us 64/3 as the area. So yeah, those are integrals. So I guess as a closing note, I like to say that calculus isn't actually as scary as people bring out to be. Like people say it's the end of math, but there's so much math beyond this. Calculus is just a tool in your toolbox to solve other problems. And in fact, many times using calculus isn't actually necessary, especially for middle school or even early high school mathematics. Using calculus, if you need it to solve a problem, you should take a break and think, hey, do I actually need calculus or can I use other techniques, such as like inequalities that you'll hopefully learn in other classes, or just using common sense triangle areas, for example. You don't need to take an integral of a triangle shape, okay? You can just take 1/2 base times height. A lot of times people use calculus, but it's not needed. And even when you need to use it, you should realize that calculus is just a tool. And that means you can apply it in interesting ways. I haven't actually showed you any problems to solve with calculus. I just showed you like remote, like integrating stuff. But it's only when you actually use calculus in a special way that it becomes interesting. So don't think you've learned all of calculus now because you've only learned the basics. You've only learned like the toolbox, but you haven't yet learned to use it. So that's my going forward note to you today. You guys should learn how to use calculus, where calculus is used, and try and apply it to problems. But hopefully you guys have learned derivatives and integrals enough that you can actually go forward and learn more. So that's going to be it for the class today. Thank you all for coming. I guess that's it. Hopefully I'll see you later in some future Math Divulge classes. Have a good day.